Thermal lilies are stupid. Okay, maybe that's an overstatement. From a science fiction standpoint, they're actually a cool concept. However, from a scientific standpoint, not so much. Now what do I mean by that? First of all, I'm not here to argue that flowers can't give off heat, or detect movement, or move super quickly. It's an alien flower, it can do what it wants. But science still applies, even to passive-aggressive alien flowers. What I am here to argue is this. If these lilies did exist the way they are currently in the game, in real life they would die within 5 seconds. But before I explain why, what are thermal lilies exactly? Well, according to the PDA, the thermal lily is an unusual terrestrial plant typically found on cliff walls. During the day, it points its face towards the sun, absorbing thermal radiation and storing it internally. At night, the thermal lily's petals close to reduce heat loss, and it relies on its heat stores to survive the harsh Arctic conditions. What the PDA doesn't mention is their main gimmick. Approaching a thermal lily causes it to turn toward you and radiate heat. Heat which is so intense that touching the lily will cause you to be burned and take damage. This begs the question, why do that? Why doesn't it just keep all the heat for itself? Well, the wiki speculates that it might be a predator deterrent, which is probably the most likely answer, even though I don't think any of Sector Zero's terrestrial fauna could or would eat them, regardless of the extreme heat. It's hard to say, but regardless of the reason, that is what they do. So, in a nutshell, thermal lilies collect energy in the form of heat from the sun, expend energy during the night to keep warm, and expend energy to radiate heat and ward off predators. But here's the problem. The thermal lilies are hot. The star, 4546, is not that hot. How is the flower able to expend so much heat energy on a predator deterrent when it seems to get so little in return from the sun? So anyway, I spent way longer than I should have calculating whether the thermal lilies could be making enough energy from the sun to counteract the large amount of heat they're giving off. The rest of this video is going to be an explanation of what I found using science and math. So after that egregiously lengthy introduction, let's get right into it. The first thing to figure out is how much energy the flower releases when radiating heat. I tried to figure this out in several different ways, but the method that ended up working the best was determining how much energy it would take to heat up robin to a certain temperature, using this heat energy formula, Q equals mc delta T, where Q is heat energy, m is mass, c is specific heat, and delta T is the change in temperature. If we find robin's mass, her specific heat, and her change in temperature, we will have found how much heat energy she is absorbing. Luckily, all of these can be found with a little estimation. The first value to figure out is robin's mass. They say you should never ask a woman her weight, which is problematic since that's exactly what we need to know. However, they don't say you should never Google a women's BMI chart by height, so we'll do that instead. According to the Below Zero wiki, robin is between 5'8" and 5'9" feet tall. According to Healthline.com, these are the healthy weights for a 20 to 30-year-old woman of these heights. Robin is clearly healthy, so these should be fairly accurate. Taking the average, we get 146.4 pounds. But we need this in kilograms, so 66.406 kilograms. That gives us our mass, and we can plug it into our formula. Next is the average specific heat capacity of a human. Specific heat is a specific value which is measured in energy units over mass times temperature. In our case, it's joules over kilograms times Kelvin. Every substance has its own specific heat capacity. In our case, we need the average specific heat of an average human. This is easy. A quick Google search reveals it's 3.5 joules per grams times Kelvin. To keep units the same, that's 3,500 joules per kilograms times Kelvin. We can now add that to our formula as well. The last thing to find is the change in temperature. I found the stages of hypothermia related to temperatures on thehikingauthority.com, something which the cold meter in Below Zero loosely follows. By the way, these are internal body temperatures, not external temperatures. You will not die of hypothermia in 95-degree weather, obviously. However, being that cold internally does present some issues. Symptoms of mild hypothermia, 95 degrees, tend to seem fairly mild. You'll start to experience shivering, general weakness, and mild confusion. letting your body temperature drop lower can be downright deadly. Below 95 degrees, you'll start to shiver, feel weak, and mild confusion may occur. Below 91 degrees, your body starts to shut down, with amnesia occurring. All sense of survival skills will be forgotten. Below 82 degrees, loss of consciousness occurs. Without immediate medical attention, death is a serious possibility. Below 70 degrees, when body temperature drops below 70 degrees, death is almost inevitable. Even though some adults have been known to survive, profound hypothermia has occurred. Since you lose consciousness around 82 degrees and are guaranteed to die at 70, I think we can say that 0 on the cold meter is somewhere between the two. I'm going with 80 degrees for simplicity. 100 on the meter equals the average human body temperature, 98.6 degrees Fahrenheit. We need Kelvin for this formula, so converting to Celsius, and then to Kelvin, gives us 310.15 degrees Kelvin is 100 on the cold meter, and 299.82 is 0 on the cold meter. To find delta T, we simply find the difference of the two temperatures, which makes out to 10.33 degrees Kelvin. Now we have all the pieces, let's put them together. 66.406 kilograms times 3500 joules per kilograms Kelvin times 10.33 degrees Kelvin gives us 2.4 million joules. That's the amount of thermal energy Robin's body receives to go from 0 on the cold meter all the way up to 100, which from what I can tell takes about 5 seconds. Now what's important to realize is that 2.4 million joules is only the amount of energy going into Robin, not the amount of energy released by the flower. Most of the heat energy would be going into the flower's surroundings rather than Robin, so 2.4 million is actually a very, very low estimate. But as you'll see in a few minutes, it's more than enough to prove my point. So now that we know how much energy the plant is using up, the question becomes, how much energy are the lilies getting from the sun? Unfortunately, there are several unknowns here concerning the way the world 4546b works. For one thing, Sector 0 is a pole, which should be getting sun for half its orbit, and not getting sun for the other half. This is because a planet's polar days and nights correspond to orbit, not rotation. Of course, Sector 0 experiences regular rotational day-night cycles like any other location on the planet, but I think it's safe to assume this was done for gameplay purposes, and so we'll disregard it. Technically, it would be possible for a planet's poles to experience equal days and nights compared to the rest of the planet. However, such a planet would be entirely unlivable. One way to have this happen would be if the planet had a 0-degree axial tilt. However, if this were the case, the temperatures at the equator would rise to extreme deadly levels, and the temperatures at the poles would drop to extreme deadly levels. Life would not be able to exist in Sector 0 without a polar tilt similar to Earth's, let alone human life. The other way this could happen is if the planet orbited the star 4546 once for every rotation of the planet. In other words, 1 day equals 1 year. However, considering 4546 appears to be a yellow dwarf like the Sun, to orbit at a similar distance to Earth and orbit at that high of a speed, the planet would be flung from its solar system. In either case, it's not scientifically possible, given that human life has to be able to exist there. You may have gathered this already from what I just said, but to support human life, 4546b has to be pretty similar to Earth in a number of ways, which means it would have to be in the habitable zone for its star. The habitable zone for a star is basically a thin strip or ring of space around a star in which the energy and temperature levels hypothetically allow for life to thrive. Earth, for example, is in this strip. This, as I alluded to before, is only one of the many preconditions of a planet for human life to exist. However, it's the only one we need right now since we're just calculating energy levels. The habitable zone is of course a very limited space, so the amount of solar energy reaching 4546b will be very similar to Earth's. The last important detail is the solar constant. This is the amount of energy which reaches Earth if Earth was an idealized perpendicular plane. Of course, Earth is not an idealized perpendicular plane, so the only place that receives this energy is a small line around the equator. Luckily, you can determine any location's energy using this constant. Earth's solar constant is 1,370 watts per square meter. Although we don't know 4546b's solar constant, like I said before, to support human life it has to be very similar. We'll be generous and round to 1,400 watts per square meter. Unfortunately for these lilies, a planet's poles actually receives the least amount of energy of anywhere on the planet. Using this formula and an average polar angular tilt similar to Earth's, we find that the amount of energy Sector 0's poles receives is 409.3 watts per square meter. The thermal lily looks to be about 1.7 meters across, which would give us an area of 2.9 square meters. However, the petals do not take up much area inside this square. So, just because it's simple, we're going to say that the flower has 1 square meter of surface area. This turns our 409.3 watts per square meter into simply 409.3 watts. But how did we do that? By using this graph of Earth's angular tilt relative to the Sun throughout the year, we can determine the average angular tilt, which when plugged in will help us determine the average energy. Hypothetically, 4546b's axial tilt could be slightly different to Earth's, which would change our final answer and screw up our results. However, Earth's Arctic Circle looks roughly proportional to 4546b's Arctic Circle. Since Arctic Circle location is directly related to axial tilt, this means both planets have roughly the same axial tilt, so I think we can get away with just using Earth's axial tilt value. Now the true average of this graph is 0 degrees, since Earth or any other planet orbits at a constant rate, at least from a year-to-year basis, and this function does not work with 0. Trying to use 0 gives an average of 0 energy, which doesn't make any sense. The planet is clearly receiving some energy. The reason this seems to be contradictory is because the graph is misleading. At a pole, angular tilt basically corresponds to day and night, which means for the first half of this graph, you will get proportional amounts of energy because the star is in the sky and is radiating heat. But for the second half, you will get 0 at all points because it is night, which means no star and no energy. To summarize, positive or above 0 tilt equals positive energy, negative or below 0 tilt does not equal negative energy, it equals no energy. Hopefully that makes sense. So what we'll do instead is use the average of only the daytime energy production. Luckily, finding the mean of a sinusoidal graph is not super difficult. To find the average angular tilt, we use this formula, where average angular tilt equals the sum of all mid-ordinates over the number of all mid-ordinates. What that means is we divide the positive part of the sinusoidal graph into equal sections, each line being a mid-ordinate. We then take the tilt values where the lines meet the graph curve and plug them in. We then divide by the number of mid-ordinates and we've got our answer, 17 degrees on average. Just as a note, this is somewhat estimated, as I drew the lines on paper with a straight edge and didn't use a computer program, but it should be pretty close. When I did it on paper, it came out to 17.0, which is the same answer we got on the other graph. Plugging in this angle, as mentioned before, gets us 409.3. Now technically, to find the true average of one day-night cycle, we would then half that number to account for nighttime. However, below zero's nights are shorter than the daytime. Again, this was most likely done for gameplay purposes, as the time difference is proportionally significant. I'm starting to feel like a broken record, but in a poll, that's scientifically impossible. The only way that could happen is if the planet's orbit was changing speeds. Technically, a planet does change its speed or velocity throughout its orbit. Planets travel in ellipses, not perfect circles, which is what changes their velocity. However, planets change their velocity slowly throughout their orbit. It's not a binary fast-slow situation. Certainly, there is no half of an orbit where the orbit is 3 times faster. It doesn't work no matter how you slice it. So I'm just not going to include nighttime at all. This gives even more energy and benefit of the doubt to the flower, plus it avoids the confusion of weird game mechanics. We already found how much energy the flower expends in 5 seconds, so let's find out how much it can produce in 5 seconds. First, we change watts into joules, which is easy since watts is just 1 joule over 1 second. Multiplying 409.3 times 5 gets 2047 joules in 5 seconds. Clearly, this is nowhere near the 2.4 million it is using up, but to put that into perspective, let's see how long it would take for the flower to generate 2.4 million joules. 2.4 million divided by 2047 is 1172, which could also be stated as the number of times larger 2.4 million is than 2047, and consequently, how many times longer it will take. So multiply that by our 5 seconds, and we get 5,860 seconds. Divided by 60 for minutes is 97.7 minutes, which means it takes more than an hour and a half for the flower to generate what it loses in 5 seconds. Remember, we gave the flower the benefit of the doubt at every possible opportunity. We didn't count energy expended during the night, we didn't count energy not gained during the night, and we rounded the solar constant up. And the biggest one of all, we calculated the amount of energy it takes to heat Robin, not the flower's entire surroundings. That could spike the energy requirement to anywhere from 10 to 100 times as much, but it really doesn't even matter. Even if we pretend all the energy released by the flower is being absorbed by Robin, it would take 10 minutes to use up nearly more than a week's worth of power, an energy store that I seriously doubt the plant has. By the way, when I say days, I mean the amount of time equivalent to one Earth day, not 4546b day. I'm unsure how long 4546b's day-night cycles are supposed to be. On one hand, it may be that 4546b rotates once every 15 or so minutes like in the game, making it one day. On the other hand, it might just be that the days are shorter for gameplay purposes. So to avoid confusion, one day equals one Earth day in this context. And that's pretty much all I have to say regarding the math behind the Thermal Lilies. In conclusion, game ruined, immersion broken. Not really, obviously. Below Zero has many flaws in my opinion compared to the first game, however, the Thermal Lily isn't really one of them. It's just fun to see if things like this make sense or not sometimes. Thanks for watching, I hope you enjoyed this video. If you did, feel free to drop a like and a sub, I would greatly appreciate it. I don't know how long it'll take, but I have several more video game related ideas I'd like to turn into videos, so expect more eventually.